Recorded is rolling. It is Tuesday, September 20th. Here's the agenda for today, and then next couple days coming up. So you guys just saw top sciences for projectile motion. You guys did real good on that, and that's again one of the hardest topics for students. So way to go there. Oh, we need to go back and talk about this mystery cut. See if you guys cracked this puzzle. Talk a little bit about pressure with you guys. We'll do a warm-up projectile free body diagram, then finish the free body diagrams from yesterday. Had a PowerPoint for you guys. We got about halfway through, about the other half today. And then tomorrow, doing different things in different classes. For AP and honors, we're doing textbook problems. For conceptual, we're doing Kahoot with Newton's laws of motion. You guys remember this packet of like 60 questions, like 20 each on Newton's laws of motion? 1, 2, 3. Okay. And then so I definitely want to do a lab with you guys. I've got a few lined up. So Atwood Lab, I'll show you guys what Atwood Lab is. We'll do this, then we'll go back and see these other ones. Okay, so at least want to plant this idea so you guys have a couple days to think about this. Okay. You guys see this pulley system, spinning wheel? Okay, low mass, low friction. Okay, you guys gonna get these in your hands. You got some string, pop the string in this groove. Looks like this, right? Ooh, right. And then what I can do is I can attach a weight to each end. Okay, so we got all these lab weights, right? Lab weights. You can start hooking these to the into each of the string. Okay, so I draw this out for you guys. It's gonna look like then is I got our pulley, string, okay, lab mass here. Lab mass here, okay. And then if you put the heavy one on top and the light one on the bottom, do you think it's gonna accelerate this way? Okay. And what if these were exactly the same mass? What if it's like 100 grams, 100 grams? What would the system do? Should be, yeah, should like hold an equilibrium, right? What if you put 100% of the weight on one side and you have an empty string on the other side? How much does this one get accelerated? The full rate of gravity, right? It's about 10 meters per second squared. Okay. Now, what if they're different? And I'll do a quick demo with you guys just to give you guys a visual. If you're watching this on video, use your imagination for a bit because we're going to go off screen here. But everybody in class, attach a couple of lab weights here. Let's do this on one side and put this on the other. Okay. So you guys can think about this. Wonder how this would work. Okay. So I got okay. So I got these two pretty close in mass, but they're different. I bring the slightly heavier one to the top. Okay. Okay. And a couple days from now, you guys get to get all these materials in your hands and swap out all the masses, and then figure out, hey, what equation, what function could govern the acceleration of the system? Right? Like if you had any journal mass 1 and mass 2, right? Then here, let the thing go. Oh, look at that. Right? You saw it accelerate. It definitely was not at the full rate of gravity, but it wasn't zero either. Right? It was definitely accelerating. I wonder how you could calculate the acceleration and how you would figure out how the distribution of those two masses would affect that acceleration. And so think about that for a couple of days. Okay. Do a lab on that pretty soon. Okay. How about that mystery cup? Where's here it is. Okay. So remember the story with this guy was got straw hole there, straw hole here. Okay. I filled it up halfway with water, and the water stayed in the cup. Functioned perfectly fine as just a normal cup. Filled it all the way to the brim, and then the entire cup drained. Right, so who figured this out? How does that cup work? Yeah.
There's a siphon.
Siphon is that? Siphon? You guys think of that? Anybody want to add to that? There. Ourselves a cup around here. So I'll draw you guys a solution. Okay. So got straw hole, so something like this, right? Right. How many guys were thinking the straw is gonna go up the side just like this? Is that what you guys were thinking? Okay. All right. Sharp group here. Okay, so let's walk through step by step. Say why would this work this way, right? And then I'll talk to you guys a little bit about pressure. Okay, so if you fill this up halfway with water, the water will stay in the cup. Now, some of the water will go into the straw, but it only fills up to like that point and then it stops. So I'll find it good. If you fill it to the brim with water, okay, now the entire straw floods. Okay, water starts pouring out the bottom. Okay, now the water drains back to the original level, but now there's a difference between this level before and this level now. There's been a state change. Now this entire straw is still flooded with water. So we got like a continuous mass. So here's where the rest of the water gets siphoned out. Oh, it's sucked out the bottom. Now here's where we got to talk a little bit about pressure. So would this cup work in a vacuum? Would it work in a vacuum? What do you guys think? So first, let me get one little technical detail out of the way that doesn't really matter. But do you guys know what water does in a vacuum at room temperature? It's going to boil. It's going to boil. So there's two ways to make water boil. One is to heat it up, but the other is actually to remove pressure. Okay, but let's say we get past that, either because it's a cold temperature or maybe some other liquid like liquid mercury. Okay, so one way or another. Okay, let's say we got some liquid in a vacuum and it actually is a state of liquid. Okay, this cup would still not work, and here's why. Okay, when this water, it's called water, why not? Right? Let's say once water level comes back down to the original level, if it were surrounded in a vacuum, then this mass would actually split and the vacuum would open up right here, which would be no problem. And then the water level would stop and it would just be like a regular cup just for half filled again. Okay. But if this whole cup is in a giant pressure, like a giant atmosphere, then this mass can't split and open up a vacuum here. Right? So it has to stay as one continuous mass. Okay. At least up to some point. Right? There's actually a limit to how much this would work. Okay. Does anybody know? Here, ask you guys a tangential question. It's going to tie back to those. Does anybody know the theoretical? Guys, why don't you learn something? Okay, are you in school? Does anybody know the longest straw you could work that would theoretically work? The longest straw, because the straw works on a pressure differential, right? Got some water in here, stick in a straw, pressure difference draws up the water. So what's the longest straw you could work that would work on Earth? How about this? Okay, here's a very similar story with the same answer. Okay. Back in the day, suppose you had a lake down here, and then there was a pretty steep mountain, and we got a town up here. Guys see a town? Bunch of little buildings. Okay. Okay. And okay, so these people in town want this water, so they start dropping buckets down and lifting the buckets, and that's really laborious. And at some point, someday, somebody invents a pump. They say, aha, we have a pump. So we can just stick a pipe down here. Okay. We can pump up this water. So that's all fine and good. Everybody's excited about these pumps. And then these mountain towns all over the place are using these pumps. Well, it was all fine and good up to a certain point, but some towns were too far above the lakes below. And there was some maximum height, H max, okay, where the water level would rise to a point and then the pressure would peter out, go to zero, and then it would just start boiling up here. Again, not because it's hot, but because there was a lack of pressure. Okay? You can't pump the water out all the way. And it turns out that height is really close to, does anybody want to guess before I give you guys the answer? What do you think? Were you thinking about 10.3 meters? 10.3 meters? All right. So it's about 10.3 meters, which is about 30 something feet. Right? That is actually one way to quantify the amount of atmospheric pressure we have. One way you can think of how straws work is that this whole atmosphere is like pushing down on that water. And it's like pushing it up into that straw, right? So 10.3 meters water. Here's another context for the same idea. Suppose this lake was 10.3 meters deep. And you dove all the way to the bottom of this lake. You guys have been in a swimming pool, right? You go down, the deeper you go, you feel that pressure going up, 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 up. Right? If you dive down 10.3 meters, you will have effectively double the pressure on you. Like right now, we're sitting in 1 atmosphere of pressure. We're definitely not in a vacuum, right? 1 atmosphere of pressure here, 1 atmosphere of pressure here, about. Right? But then if you go down 10.3 meters, you get to like 2 atmospheres of pressure. Ooh, so you like add an atmosphere just from water. Right? if you did this with mercury, you guys know mercury is a very dense liquid, right? Very dense liquid. It only goes up about 76 centimeters. So that was a way to quantify atmospheric pressure. Okay. Well, let's quantify one atmosphere a few different ways then. Right. So we've got one ATM, one atmosphere. Right. You could call it 76 centimeters of mercury. You could call it 10.3 meters of water, just like as a liquid column. Okay. Well, what are some other ways to quantify pressure? What is pressure? What are the units for pressure? I mean, one unit is atmospheres. What do you say?
Um,
Newtons per square meter. Newtons per square meter. You do that. Okay. It's also called 1 Pascal. Okay. There's another way to quantify too, but let's go with that one. I like that one because that's metric system, right? Okay. Does anybody know? Let me give you guys context for that. Newton per square meter, right? So 100 grams. This weighs how many newtons about? Dang it. One Newton. So 1 Newton is actually 0.98, but let's call it 1 Newton. So it's 1 Newton of gravity force flowing down, right? Okay. And take a look at these floor tiles. Here's a meter stick. Floor tiles. Meter stick's a little bit more than 3 floor tiles. Like that. So if you rope off 3 floor tiles by 3 floor tiles, that's pretty close to a square meter. It's a little bit less than a square meter, pretty close to a square meter. Okay. Meter's a little bit more than a yard. Okay. So if you had the weight of this pulling down on 1 square meter, it's supposed to be like a foam board that was 1 square meter, right? That would be 1 Pascal worth of pressure, 1 Newton per square meter, right? Here's that square meter. Here's this little lab weight sitting right here in the middle. It's 1 Newton down on 1 square meter. That could be 1 Pascal, right? 1 Pascal is 1 Newton per square meter, right? Now, what is 1 atmosphere? How many of these? How many of these pascals is 1 atmosphere? Anybody want to guess? How many of you guys were thinking 101,000 Pascal? Whoa, that's crazy. Like 100,000 of these on every square meter? Huh. Right. Does it? What's another way to quantify pressure? When you guys pump up your bike tires, I have a gauge on it that says PSI. So like pounds per square inch. Right. And 1 atmosphere, 101,000 pascals is equal to how many pounds per square inch? It's about 14.7 PSI, which is pounds per square inch. That's what PSI is, right? Pounds per square inch. Okay. Guys, how much does a bowling ball weigh? About 10, 15 pounds? Whoa, 10, 15 pounds per square inch? Here's a square inch. It's pretty close to a square inch. I had a bowling ball. You guys have a bowling ball worth of atmospheric pressure on every single square inch of your skin? Yes, you do. That's a lot of pressure. Like you would notice it if you like step into a vacuum, like whoa, it's all gone, right? But it's a lot of pressure, right? And so enormous amount of air pressure that we're in. Here's different ways to quantify this. Okay. And again, how it translates back to like the straw, it's about 10.3 meters column of water. Okay. Hey, suppose you made one of these Pythagoras cups, okay, and you made the world's largest Pythagoras cup. It was some kind of roadside attraction out by the interstate. Okay. What's the longest straw you could theoretically have? 10.3 meters, right? Yeah, if you make it that long, it's probably not going to work. Water level's kind of just stop right there. All right. Any questions about pressure? Right, so fun little side quest there. You guys learn a little about pressure. Okay, let's do this free body diagram on a projectile. Free body diagram. Okay, so yesterday I did a bunch of free body diagrams with you guys, and we're going to do more today. Let's just start with this one. Okay. So I got a cliff. Okay. Let's put this cannon on this cliff. Okay. And then blast a cannonball. Yeah, look at this cannonball at different parts in its trajectory. Okay. Maybe I take a snapshot every second and something like that. Okay. Can you draw a free body diagram for each cannonball? And we give you guys a hint here. Let's say ignore air drag. Okay, so ignore the fact that it's plowing through the air. Maybe this is a vacuum or air drag is negligible. Right? Okay. Now, guys, free body diagram means you're drawing what kinds of vectors? Do you care about velocity vectors? Diagram. Do you care about displacement vectors? Do you care about force vectors? Yeah, that's what you care about. You care about force vectors, right? Okay, now, this first cannonball here has already left the cannon barrel. Notice I didn't draw one inside the cannon barrel because there would definitely be like a blast force pushing up to the right. But now it's no longer under the influence of that blast force, right? It's just moving. Isn't this cannonball in free fall? Right? Now, it's moving up and to the right. So if I drew a velocity vector, it'd be a velocity vector over to the right. But that's not part of the free body diagram because I care about force vectors. Right? So what's one force on this cannonball? Is there any force on the cannonball? Yeah. And what is it?
Gravity.
Yeah, it's weight. Yeah, so yeah, I guess you could say 10 meters per second squared times its mass. Sure, you could say that. Okay. So I'll label that mg, right? Mass times gravity field. If you want to just do F sub g, the force due to gravity, that works. In fact, if you want to just write out the word weight, that would work too. Okay. So that works, that works, that works. You know, if you're labeling these forces, right? More often than not, I label it mg. I've just always done that. Are there any other forces on that cannonball? Yep, that's it. That's the whole thing. What about when it gets up to here? What force is on a cannonball?
Energy.
Yeah, mg. Anything else? Nope, that's it. What about right here? Mg. Hey, does every single one of these cannonballs have the exact same free body diagram? Sure does. Oops. Mg. Yeah, that's it. There's all 5 of them. They're all exactly the same. Okay. Okay. Yeah.
Why aren't we accounting for the movement to the right?
Okay. Because the cannonball being in motion, that's velocity. Okay. Now, if I did do velocity, do velocity. Here's velocity. Now it's like changing direction and probably picking up speed. Probably moving a little faster right here, and then really fast here. Velocity, right? Okay. But velocity is not part of the free body diagram. Okay. So in fact, you don't even have to draw that. It's not even part of the diagram. Okay. Okay. So our free body diagram, all you care about are what forces are acting on it. In this case, there's only one force. Okay. Now, suppose you did put in air drag. Okay. In that case, you might care about velocity because air drag is always going to oppose the motion. So when the air drag like point opposite of the motion, right? That'll show up on the PowerPoint later, but we'll do one of those. But for now, if you ignore air drag, there's only one force. It's just its own weight. That's it. It's the only force. Right, now, at some point, it's going to come up anyway. So let me ask you guys this. You guys remember doing Newton's laws of motion? And there was this third law of motion that everybody can say the words, right? For every force, there's an equal and opposite reactive force, right? But sometimes it's tricky to pick out exactly what that force is. So I'm going to see if you guys can figure this out. This cannonball, well, actually, I guess any of these, right? You can pick any of these. Okay. Has a force pulling down, like the Earth is pulling this cannonball down with so many newtons of force. What is the equal and opposite force to this force of the Earth pulling it down? If the Earth pulls the cannonball down, what's the equal and opposite force? Yeah. Okay, it is equivalent to mg because of equal in magnitude. Okay. Oh, opposite direction. So that'd be something pulling up, wouldn't it? I mean, here I'm showing a downward force. So there must also be an equivalent upward force. What is that equivalent upward force? What's pulling up? See, the Earth pulls the weight down. Hey, does the weight pull the entire Earth up? Yes, it does. But which force is bigger? The Earth pulling the weight down or the weight pulling the Earth up? Wait, didn't you just tell me they're the same? Yeah, equal, right? Equal? Okay. Okay, so right now, the Earth is pulling this 1 kilogram mass with 10 newtons of force. And so if I drop it. It's going to free fall at 10 meters per second squared. Now, Newton's third law is not necessarily super intuitive because you might think, well, the Earth doesn't really move, right? Well, due to this weight, right? Which is pretty much true. But for that explanation, you actually have to take back to Newton's second law of motion. So let's take a look at that. Okay. Remember, it's equal and opposite forces, so they have the same force either way. Okay. This is being pulled down by the Earth with 10 newtons, but it's also pulling up on the Earth with 10 newtons, so it's 10 newtons either way. Okay. Now, if I let this free fall, 10 newtons acting on 1 kilogram, which is exactly what this is, right? Let's it free fall at 10 meters per second squared, right? 10 over 1 is 1, right? But what about the Earth? That same 10 newtons acting on the Earth, pulling the Earth up, acting on the entire mass of the Earth, is what happens when you divide by a number that's like bajillions big. What is suppose you buy a lottery ticket and there's a chance of winning of like 1 in 20 million. What is 1 over 20 million? It's very close to zero. That's why the acceleration of the Earth due to this movement around is like pretty much zero because the mass of the Earth is so much. The Earth has so much inertia. I see that? All right. You guys ready to move on? Okay, so let's flip the screen here. Go over to PowerPoint. Oh, whoops. I have to go way back. I don't see any of these yet. All right. So yesterday, there it is. Okay. That's the one we left off on yesterday. Remember the rocket moving at constant velocity through space? I said, what's the forces on the rocket? You guys said, well, there are no forces. It's just moving because of inertia. It's just going, right? See, if it was blasting its engines, that means it would be accelerating, which would not be in constant velocity anymore, right? So just like Voyager spacecraft, it's just going because it's just going. It's just inertia, right? There's no force change in its motion at all, right? No force. Right? All right, new one. And if you guys need paper, you guys see this front two desks right here. There's a stack of paper. You need some paper for your notes. This PowerPoint is also posted to the classroom if you want to download it from there. But that's a good idea to take notes, build neural connections in your mind too. Air hockey puck moving across the surface at constant velocity. Let's ignore the little tiny force of air drag as it's moving around. Okay. But so, hey, constant velocity. Constant velocity means the acceleration is 0, which means the net force is 0, right? So I bet all the forces should balance out, right? Okay, so I see that air hockey puck moving left to right on the screen. What are the forces on it? What's one force? Does it have a weight pulling it down? Yeah, it's got weight pulling it down, but it's not a free fall. Do you guys think there's an upward force? Maybe from the air jets, force from the air jets, right? Well, those are balanced out. So I think that satisfies that white text up there. Is that it? Are there any other forces? No, that's it. Okay. Now maybe you say like when you're hitting it, it's there's the force of hitting it. Okay. But that's getting into motion. That's not constant velocity. Okay. Now once it's left the I just don't know what thing's called. The paddle. I don't know. There. Okay. Well, once it's just in motion at constant velocity, that's it. That's the answer right there. You're looking at. Okay. Guys good? Okay. Next one. Ooh, the Earth and the Moon. All right. So I'm sort of laying the groundwork for some future content that you guys are going to do a few weeks from now. You guys know this is going to be an orbital situation, right? We haven't quite got to orbits yet, right? But we can at least actually set up actually a pair of free body diagrams. There's one for the Earth and one for the Moon. Let's treat this as a closed system. Just say that we just got the Earth and the Moon. Let's ignore everything else in the solar system, right? Right. So in the next few weeks, I'm going to have you guys eventually do a lab where, well, if there's some kind of orbiting going on, there's going to be something called a centripetal force, right? And that centripetal force is related to, what's it related to? It's going to be related to the mass of the object that's revolving. It's going to be related to the speed that it's going around, and also the radius of curvature, in this case, the distance between the Earth and the Moon, right? So that's future content, just planting some ideas today, right? But if you're just focused on the forces, which is the purpose of this activity, right? We're just focused on the forces. Okay. Guys, does the Earth pull on the Moon? Yeah, right. Isaac Newton was thinking about that. Remember, Isaac Newton saw the apple fall and looked up in the sky and saw the moon and said, aha, he was the first guy to make the connection that it's the same phenomenon, right? There's some kind of pull going on. Okay. How about this? Does the moon pull on the Earth? Does the Earth have tides? Yeah, that's mostly caused by the moon, right?
Huh. Okay. So the Earth pulls on the moon pulls on the Earth, but which force is bigger? For every force, there's an equal and opposite reactive force. Hey, we're about to have an action and reaction force pair, aren't we? Right? Did you guys say? Here, I'll give you guys the answer. Did you guys say that right there? There's a gravity force both ways. Right? The Earth pulls on the moon pulls on the Earth. Notice those are exactly the same magnitude. Right? But to go in a little bit too much detail, there's actually what's called a barycenter that both of those objects revolve around. But the barycenter is so close to the center of the Earth that you can, what we're going to do for the rest of the year is just treat it as basically the center of the Earth. Yeah. All right. So yeah, and for the orbital mechanics, if you give that moon a tangential velocity to the side fast enough, then it'll this gravity force will act as the centripetal force and it'll hold it in orbit. All right. So speaking of centripetal force, some of these are about top, not on this slide, but we're going to do a few that involve this roller coaster. Right? You guys been on a roller coaster? Right. Some interesting dynamics going around. Let's say it's at the top of the hill, and it's just like click, 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 just real slow, and it's about to crash. Right? But it's just real slow right here. Right? Basically parked. Do you guys say that roller coaster has a weight acting down, and also what's keeping it up? The what kind of force? You guys say the normal force? You guys remember that? Normal force, right? So that's from the tracks, right? Now, those I have as equal not because of Newton's third law, right? Remember, Newton's third law, you need two different objects. So the third law force of the Earth pulling the cart down is the cart pulling the entire Earth up, right? Which is not shown here, right? And the opposite force of the track pushing the cart up is the cart pushing the track down, right? So we're not worried about, we're just focused on a single object, which is just the cart itself. Okay, roller coaster at the top of the hill. Right. All right, so those are balanced. It's basically at rest and it's ready to plummet. Right, now let's let this thing go down. Okay, let's say it gets all the way down to the bottom. Now I drew a velocity vector to give it some motion, which will affect the answer. But remember, velocity vector is not actually part of the free body diagram. Right, I'm just saying it's there. Now this is getting into, again, future content. We'll do this a few weeks from now. But see how that cart's on a curved path? Right? See, if it was on a straight path, it'd have the same free body diagram as the last one. Weight down, normal force up, balance out, done. Right? But do you guys see how as that cart moves to the right, it's also at the same time going to be forced up into a loop? Right? So there must be some force that causes a change in direction, which kind of reminds me of the orbiting moon situation. The moon is constantly changing direction as it's orbiting the Earth. And this is very similar to that. It's on a curved path, right? There's some kind of centripetal force going on, right? Centripetal force, right? So how are we gonna get that? Well, do you think this car still has a weight pulling down? Okay. And do you think there's a normal force from the track? Right? But if you guys are sitting on that car, do you feel really light or really heavy? I think really heavy. Yeah, really heavy, right? Right. And it turns out normal force from the track is greater than the weight of the car. You guys see that? Right. Do you guys see that there's going to be a net force upward? Hey, is that cart right there in equilibrium? It is not. There is a net force on it. And the net force is upward, right? Normal force minus the weight. Right? And that net force is called centripetal force. And then we're going to say what has to do with the mass of the car, the speed of the car, and the radius of curvature. See if you could kind of estimate the radius of that curvature. Right? There's an equation that ties all those together. Then I'm going to have you guys figure out for yourselves. I'll give you guys the lab equipment to figure it out. Okay? You guys good there? And that's it. That's the entire free body diagram. Okay. Let's do one more roller coaster. Let's take this to the top of the lid. Let's say it goes around relatively slowly. Right? So it just kind of barely makes it around. And if that's true, if it just kind of barely loops around, do you feel really light or really heavy at that point? Well, you would feel really heavy if it zoomed around really fast. Sorry. Zoom. Yeah, that is true. But if it just kind of like you think you'd feel kind of like an astronaut for a moment? Yeah. You gonna say that? Kind of closer to an astronaut? So I'm thinking you feel pretty light at that point. Now, does Earth still pull on it exactly the same as it did the last couple slides? It sure does. So the weight never changed any of the last three slides, right? The weight's still the weight, right? Hey, which way is, let's say there's a little bit of force from the track pushing on the cart. Which way does the normal force push on the cart? Ooh, same direction as the weight in this case, right? In fact, if you add those two in the same direction, then that could represent that centripetal force I keep alluding to, that there's going to be an equation for later in this semester. Okay. You guys good? Which you might have printed materials on from first day of school if you're really curious and want to look ahead. All right, let's go back. All right, let's get rid of all that centripetal stuff. Let's go back to classic car brakes to a stop. Okay, so I see that car going left to right, and then brakes to stop. So what's one force on this car? You have a weight pulling it down. Okay. In fact, if it didn't, then if it's just floating around in space, you can't really have anything else. So it's got to have that to kickstart everything. Okay. Hey, what's holding the car up? Normal force from the road. Bam. Okay. Now, if I just did that, walked away, the car would be going constant velocity. But oh, I said it's going to be braking to a stop. So what else do I need? Yeah, what do you think? Friction. And which direction should I draw the friction? You're saying to the left? Left? All right, yeah, I see a few of you guys saying to the left. And you are right. Look at that. That's it. You guys nailed it. Here's the free body diagram. Car braking to stop. Okay. So it has a rightward velocity, but it has a leftward net force and therefore a leftward acceleration. Right? And you guys remember that whenever velocity and acceleration have opposite directions, that's a slowing down situation. Right, take this one. All right, now this one I want to talk about a little bit more because I think you guys probably just about got your driver's licenses. And one of the things you guys had to learn about to get your license was something called anti-lock braking system. You guys learn about anti-lock braking? All right, let me tell you guys the physics of that. So this friction force and this normal force, if you take the ratio of those, this friction divided by this normal force, that is an important ratio in physics. It's called the coefficient of friction. And it turns out there's actually two different categories of coefficient of friction. There's static friction and kinetic friction. So suppose this car was parked and you were given a push to overcome the initial friction. Well, that would be a static case because the tires in the road aren't pushing against each other. Right? Versus if the car is sliding across the road, either skidding across or you are pushing it across the asphalt and the tires are going, that's a kinetic case. Right? Guys, what do you think? Which value do you think is bigger, static friction or kinetic friction? Show of hands. How many guys think that, regardless of the materials, because this is a material property, how many guys think that static friction is consistently larger? Static friction is greater than kinetic friction. If you're thinking that, then you are right. So static friction is. Okay. So I'll give you guys a numerical example. Suppose this friction force was like 500 newtons and the normal force was 1,000 newtons, right? So 500 over 1,000. Hey, is that 0.5? Right. Maybe call it static friction. Right. Versus if the car is skidding, like that would definitely be like a sliding case, like kinetic friction. This might only be 400 newtons, and then 400 over 1,000 would be like 0.4. So coefficient of static friction could be 0.5, and coefficient of kinetic friction might be 0.4, right? Right. But static friction is always going to be more than. Right? Hey, if you want to brake this car in a hurry, you want it to come to a stop in a short amount of road as possible, would you rather take advantage of the larger amount of friction, which would be the static friction, wouldn't it? Right. So do you want the tires to maintain some kind of traction to the road, or do you want it to be sliding like, I'm thinking if they had some kind of traction, that would be taking advantage of static friction, which is the greater value. It'd stop the car sooner. Okay. And the way to do that is to not actually lock the wheels. Hence anti-locking. You see where this is going, right? Anti-lock braking. Okay. But to actually allow the wheels to rotate forward just a little bit, right? As the car is stopping, right? Which might be counterintuitive because wait, I'm trying to stop this car as soon as possible. I want the wheels to rotate forward a little bit. How does that make sense? Because that allows you to maintain some kind of static connection with the road. Okay. Now, there was an old way this worked and a new way this worked. The old way, suppose you hop in a time machine and go back to the 1970s. Right? Now, don't follow this advice I'm about to say. This is real old advice. Is they said don't slam the brakes, but they said to like pump the brakes. That was the old advice, to just pump the brakes. And that for that reason is that you're trying to avoid skidding and maintain some kind of static friction with the road, which will stop the car sooner. Right? Now, the new advice is just go ahead and slam the brakes, just full on, because your car has a computer system in it that will take care of that process for you. And the name of that computer system is anti-lock braking system. Okay. You guys good? All right. Next one. car goes around a curve, as seen from behind. Can you guys imagine a couple taillights right here? See some taillights, right? Watching this car from behind. Right. Let's say the road is flat. Right? I mean, if it was banked, it'd be easier to make the curve. But let's say the road's flat. Does this car have a weight down and a normal force up? Right. Right. Now we're looking at the taillight. Suppose this car is making a left-hand turn. We're watching it turn left. If the car is changing its direction to the left, what force do you think is allowing it to do that on a flat road? Huh. You know what, if the road was iced over, would it be really hard to make that left-hand turn? It would, because there would be hardly any friction. So it is a friction force in this case, right? And which way should you draw that friction force if it's forcing the car to turn to the left? All right, how about to the left, right? Yeah, right. Okay. Oh, block hanging at rest from a spring. Is there a weight pulling the block down? Is there a spring force holding the block back up? Right. And I told you guys a little bit about Hooke's law, F equals kx. Right. So, I bet that spring has some stiffness. There are different kinds of springs. You guys got different spring scales when you guys did this lab, right? The amount that stretches. I bet kx is balancing with that mg. Solve for stuff. A bottle rocket blasting upward through the air. Here, I'll go and give you guys this one. You guys think that there's a here it is. A thrust force up and then maybe a weight acting backwards. And if you consider air drag, then the drag is going to be opposite of the velocity. So that would also be this way, right? Okay. Hey, is that rocket right there in equilibrium? I don't think so. I think there's a net force. You guys see the thrust force beats the combined weight and drag force acting backward? Right. I think that rocket right there is still accelerating. I think it's accelerating forward or upward. Here, I promised you guys we would do this one. All right, so let's do a ball flying through the air. Right. Very similar to what I did on the projection at the beginning of class. But now let's say that there is air drag. Right. So does that ball have a weight pulling down? Yeah. Right. In fact, that's the entire time we did projectiles, that we were just considering that situation right there. If that's all there was, it'd be a perfect parabola, right? That's how you get a perfect parabola. But if you also include air drag, which direction should you draw the air drag? Down to the left? You guys saying down to the left? Yeah, because it would be opposing the velocity, right? Now, if you're thinking ahead a few steps, we're not going to get this tricky in this class, but just thinking how this would work. Isn't that drag force constantly changing direction as the ball changes direction? Right? And also isn't changing magnitude. Did I tell you guys yesterday with the parachute that the drag force is proportional to the square of the speed? Right, so that could be pretty tricky mathematically, but yeah, just food for thought, I guess. Pulling a stubborn donkey. You guys think that there's a tension in each one of those ropes? Tension, right? And if the donkey's not moving, you better be in equilibrium. Hey, do you think there's a friction force? His hooves are dug in. It's the opposing those tensions, right? Now, if I did this exactly right, then the left component of this tension, the right component of this tension should cancel out. The left and the right should cancel out. And also the two forward components should cancel out with the backward component. I think I need to redo that vector a little bit, but yeah, kind of close. I think I missed the mark a little bit. But the two forward components should balance out with the backward component. Okay. All right, and here we go. Here's our. We're going to spend a few minutes on this one. A block at rest on an incline on a ramp, okay. Which I made a whole poster for. You guys see that poster right there above that door? Okay. So that's the answer. But I want to walk you guys through this step by step, because this one takes a little bit more thinking. Right. Also, there's a lab I'm going to have you guys do probably next week. That's going to involve that scenario. I'm going to have you guys take a lab weight, put it on your desk, tip your desk up until it starts to slide off. But she does look a lot like that, doesn't it? Yeah. Right, so you guys got some rulers? Need some rulers for this activity. We're doing okay. Yeah, we're doing all right on time here. Right, so let's draw this incline. Draw an incline. Got some angle going on right here. Label that theta. Right, that's so many degrees to the horizontal. And throw a block on it. You know what else this kind of reminds me of was one of the first labs you guys did in this class, which was remember those Hot Wheels cars? Okay, if I put little wheels on this, or I say a frictionless surface, which are pretty similar to each other. Okay. It does kind of look like that too, doesn't it? You guys had an incline,
car accelerated down. Right. Now, whenever you have this scenario, so a block on an incline, always do this first. We're going to introduce a new Cartesian system that's going to run parallel and perpendicular to the surface. Not parallel and perpendicular to the ground, not parallel and perpendicular to gravity, but parallel and perpendicular to the surface. Because the motion of this block is effectively constrained somewhere along the surface. It might be sliding this way or this way. It's going to be sliding along its axis. Is that true? Okay. Now, there could be 2 or 3 forces acting on this block. Okay. What's a good force to start with? What's one force on this block? Yeah, it's weight acting straight down. Yeah, weight straight down. Okay. In fact, we have to have that one. If we don't have that one, just float around in space. We don't have anything else. So let's definitely get a weight acting down. Okay. So I like to label weight mg, like mass times gravity field. So I'll just go and do that. Mg. Okay. Now, notice that that weight is not aligned to that rotated Cartesian system that I just made a whole big deal about. Okay. So we're going to have to break this in. There's some other forces too, but we'll get to those later. Okay. We're going to have to break this weight into components that align with that coordinate system. Okay. Do you guys see how the weight is mostly pushing this block into the surface, but it's also partially pulling the block along the surface, right? And that's exactly the components we're going to do. So I'm going to make a right triangle. I'm going to dash this component. Say, here's how much this block is pushing into the surface. Okay. This is that's kind of hard to tell. I've got 1 dash for the axis, 1 dash for this component. This weight component. There you go. Okay. Look, component right there. Okay. Notice I didn't make it solid because if I made it solid, I'd be double counting it, but I dashed it. And then part of its weight, one component of this weight, is actually pulling it along the surface. All right, now for this one, you guys see how I'm holding my ruler parallel to the surface and parallel to this axis? You guys see that? Okay. Am I holding my ruler parallel to the ground like this? Bing, bing, bing. Can you guys do parallel? Okay. A lot of students, just so over the years teaching this class, struggle with this, making parallel lines. Can you guys do parallel to the surface? Okay. So right now, is your ruler parallel to that surface? Okay. And now, once it is, you can dash off this component. Bing, just like that. Okay, is that a little skinny right triangle? Do you guys see where the right angle is on that right triangle? Is it right here? It's right there, isn't it? Is that right angle? Is that? Okay. How about this angle right here? Ooh, guys, is this angle same angle? Let me see. They look like they're the same. This one is 29 degrees. This one is, oh, that's 29 degrees too. They're both 29 degrees. 29 degrees, 29 degrees. Okay. Now, convince you guys a little bit more. There you go. Okay. Let's do an animation. Can you guys animate your mind? Suppose I have an incline and ramping it up. Okay. Now all these blocks have the same weight, the exact same weight vector pulling down, but they're split into components differently. Now this one's 100% of its weight pushes into the incline. But this one, see a little skinny wedge here, a little skinny wedge here. Okay. Ooh, see 45 degrees here, 45 degrees here. You guys see about 70 degrees here and 70 degrees here. It's the same angle, isn't it? All the way across. Okay. Also, as you ramp the incline, you guys see how the amount pushing into the block gets a little bit less, a little bit less, a little bit less. Now here it's really small. The wall will shrink to 0. Right. And there's more and more component that pulls the block along the incline. Ooh, interesting. You guys see that? Okay. So there. Okay. So just to move us along a little bit. This component here is mg times what? Sine or cosine theta? Mg, it's opposite of the theta, which makes it sine, mg sine theta. And this component must be mg cosine theta. So all that trigonometry is coming back. Right? Again, right, keeps coming back. Hey, is there some support force from the incline holding the block up called the normal force? But hey, that word normal, that means perpendicular, doesn't it? Right. Now, if it was a flat surface, it would just be straight up. Okay. But this is not a level surface. This is an incline. Okay. So the normal force is going to point off in this direction. I'll call this F sub n for the normal force. Okay. But do you guys see that normal force is going to be equivalent in magnitude to mg cosine theta? Right? mg cosine theta. Is that? Okay, now, if I just stopped right there and walked away, this actually would be the free body diagram for your Hot Wheels cars, right? Because these two cancel each other out, right? This component of the weight and this normal force cancel each other out. Block doesn't move into or out of the incline. Okay? And what's left over would be the mg sine theta. That's the net force. That was what was pulling your cars down, was mg sine theta, right? Is that? Okay. But let's go one more step, which is if the block is at rest. Now, if the block is at rest, or if the block is moving down at constant velocity, there's both cases of equilibrium, right? Either at rest or constant velocity. Okay. So I need one more force, which is the friction force, which is going to be exactly opposite of mg sine theta. So it has that magnitude. So I got force due to friction. I drew it this way. I'm going to call it mg sine theta. And this could be either a block at rest. Here, spell that out. Block at rest. Or block moving at constant velocity. Okay, this could be the free body diagram for either one of those. Okay, maybe this one's static friction, this one's kinetic friction, but otherwise they look pretty well the same. All right, you guys have a great rest of your day. Thank you.